Okay. Going to be covering acid-catalyzed hydration. So this is, see it, number 2. So the idea behind acid-catalyzed hydration, similar to hydrohalogenation. All these concepts are very similar. So we're now like, you need water, you need acid. Acid-catalyzed hydration, water. So let's just say favorite acid, H2SO4. I love sulfuric acid for some reason. Sulfuric acid. And I'll give we need water. So right. So for hydration, we want an excess of water because we're going to be. We'll see. I can also show the reverse reaction for dehydration. That the reactions are very similar. You basically just run it backwards. Yeah, just what matters is your concentration of acid or your concentration of, or your, like, how much water you have. Anyways, this is also a Markovnikov reaction. So look at this. I hope it shows. So this is another, I'm gonna abbreviate Markov because too lazy. Markov. So here's a medic. So I chose a strong acid. The idea is that the acid will dissociate, so we'll have free hydronium ion, free H pluses, and H pluses essentially functions as an H3O, is our goal here. So we'll have an H3O, H2SO4 will go to H3O. So this is actually like a lot gnarlier mech, I might say. H3O, visible. So we learn from just like bonding and stuff. Oxygen prefers to have 2 bonds because it's got 6 valence electrons usually, and it prefers 2. So even though we have a lone pair here, what's happening is this lone pair, this bonding pair, come out here, any of the hydrogens really grab it, and this one's over here. Boom. So this hydronium is going to turn into a water, and that's going to result in this. So this hydrogen is going to go here, right? We have another case of Markovnikov, and we're going to have the carbocation right here. And then we have H, O, H. And there's another way we can restabilize this again. This lone pair over here, and we get right? And the reason why we do this in excess of water is because we're going to need water again to take out one of the hydrogens. So this water is going to take out one of the hydrogens here, stabilize it, boom. Because this is a positive charge right now, right? It's got 3 bonds on it. So it's got 5 electrons basically. And then we're going to have this. O, H, plus H, O, H, H. Oh, I did the big donut. There we go. Right? So this, essentially, we don't need too much acid because, as you can see, the hydronium gets recycled every time. And yeah, so that's acid-catalyzed hydration, and it's hydration because we added H here, OH here, which is an addition of H2O to it. And yeah, that's also why we need an excess of water to match with everything in there that needs to be hydrated. Okay. I don't know, do I have any hydration reactions? Acid-catalyzed hydration. Let's see what I can pull up. Okay. Do like 5 questions. Number 1. Do an easy one. Actually, because the mechanism I showed you is really simplistic, this is the same mech. I'll do a harder one a little bit. Let's skip the first question. That. Acid-catalyzed hydration. So here, you use sulfuric acid. You can use any acid. You can use hydrochloric acid. Honestly, anything that gives you an H+. We just want that free H+ ion. That's all. And we start. Right, and then we go to H3O. Complete your full charge. This grabs the hydrogen, goes into the oxygen, and we get so let's look here. This has no hydrogen, so this is one hydrogen. So this is our carbon again. The hydrogen's gonna go to this one. So we're gonna have a positive forward charge right here on this carbon right here. So your tertiary carbon cation, which is the most stable once again. They're empty pure, real basically just get filled by like bonds and shit. Hella. Just cool stuff. And now we have water, right? I just draw so I can have my lone pairs close and it fits the paper wall. So here, right? And now we have this. Positive charge on the oxygen. Don't worry, oxygen. Bring more water to the rescue. More water, more water. Also, lucky me, there's no chirality on this one, right? Right? A bond pair on this oxygen is going to take that hydrogen. This bonding pair goes over to the oxygen, stabilizes it. Well, gives it a, neutral charge, which is ideal. And now we have our product. Leads us to I'm going to abbreviate this H2O because I don't want to write it plus. So, what can happen is there can be chirality and enantiomers on these. I got lucky that there were 2 methyls, but if it was like this, you know, then I'm so funny. This is even achiral. Just keep on adding. There we go. Then this could have some enantiomer. We could have an R config here or an S config, and this should not be shouldn't be enantioselective. It shouldn't. I think we say stereoselective. Regioselective? One of those. Regioselective is when you only get one certain product over the other products. And this is enantio. Anywho. Let's do one more. Favorite acid, H2SO4. I love it. Favorite acid of all time. First step, you always just draw your hydronium. Every time. Just draw your hydronium. Right? Always this. Always that step. Always. All the same shit. So, let's see. Where does the hydrogen want to go? It could go in either, right? Interesting. I think I'll go with this one. Because this is, you can spread better this way. In my opinion, at least. My humble opinion. I don't think it makes a huge difference. Because we're going to see the same shit anyways. Specifically, if I stabilize the carbocation, methyl shift. Right? Yeah, because if it ends up, even if the positive charge is like, alternatively speaking, even if the positive charge is right here, we'll get a hydride shift, right? This hydrogen will move here, this positive charge, and then we're back to here. So we'll have the, you know, we just want to get this positive charge onto the more stable, more substituted carbocation. That's what we're ideally looking for. So, not even an issue. 1,2 methyl shift. I clearly cannot spell clearly. It's good though. Right? So we're gonna have and you have the methyl now. And the positive charge is now arrived here, right? Yep. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. We're good. Remember this, buddy. tertiary carbon cation. Immaculate vibes. OH. Give him more water. This boy thirsty. He's thirsty. Right? Water grabs another hydrogen. And we get ta-da! And that's our product. Oh. The stroke is tiny. Boom. Acid-catalyzed hydration in a nutshell. So I was thinking about this. Oh, good question. Just a hypothetical, I think. The mechanism is always similar vibe, but I think we can undergo two catalyzation, acid-catalyzed hydrations if we have something like this. Just throw those right there. You know, where we get to yeah, like I would presume that if we had this excess H2O, you would probably get something like this. How would I do so many? That we would get like a metal shift probably. I would say no, we wouldn't get a metal shift. We would get a hydride shift, right? Okay, this one is pretty clear that the hydrogen will just go here, the oxygen, the hydroxyl goes here. So we're gonna have that's clear. With this one, the hydrogen will go in either of these two, or we're gonna get a hydride shift, a second hydride shift to get the carbon cation right here again. And then we will get that. Or actually, what if we had a methyl shift? Like, what if we had this as our intermediate? What if we had, if it went through this one first, right? What if we had this as an intermediate? And this methyl shifted over here, and then we got, no, you don't want that actually, because even though this is a tertiary carbocation, it's got a hydroxyl on it compared to a carbon on it, and this is more, this helix electron's harder, so we're gonna get this product. This top product will be the primary product for that one. Acid-catalyzed hydration.